How's it go? The mapping AB maps to AB inverse is continuous, right? I keep spelling continuous. I should just always go there. Duh. And of course, that map is from where? G cross G to G, right? So that's a topological group, and he gives some examples of topological groups. Three nice examples. I think these are great examples. Really nice. Big GL and R, big GL and C, and then just a Euclidean space with addition. So each one of these is a topological group. What does GLNR mean? Yeah, so it's like, well, yes, general linear group. You're right. So A and R n by n such that what? Such that the determinant of A is what? Non-zero. Likewise, GLNC, A and C n by n such that the determinant of A is not equal to 0, right? Now, these are subspaces of, so this is like an arbitrary Euclidean space. So an example of case 3, for example, you could look at R n by n. You could look at C n by n. Just a set of square matrices with real or complex entries. These form vector spaces, right? And in fact, topological spaces, where the addition operation forms an abelian group, and that is so these are topological groups. So you can also look at the topology of GLNR as it appears. I mean, GLNR is a subspace of what? Of what space? What's that? Matrix group. I mean, this is the... Okay, yeah, it's a subset. Right, by construction, it's a subset of Rn by n. What's the topology in Rn by n? So we could say Rn by n, Euclidean topology, has, what's the norm? How about this? It's the trace of A transpose square root. This is just a very elegant way of writing out the square root of A11 squared plus plus ANN squared. That may not be obvious to you, but it's true. That's the norm on n by n matrices. It's just like taking the matrix and stringing it out into an n squared vector and using the usual notion of vector length, so-called Frobenius norm on matrices. All right, so that gives a norm to Rn by n, and with respect to that norm, we induce, the structure of a Banach space. Actually, right? It has a norm. It's a complete normed linear space, n squared real dimensional, and GLNR is a subset of that, right? And so my question to you is, this GLNR, is it open? Is it, what kind of set is it with respect to that topology? Could you have any idea? You'd say closed. You believe I believe the determinant is continuous as well. I completely agree with you. And you have been seduced by the equality on the board and neglected the fact that it is an inequality. And you have the right idea, because this is, in fact, the inverse image under the determinant of what? It's the inverse image of the determinant of numbers which are non-zero, which is what? Minus infinity to 0, union, 0 to infinity, yeah? And you're suggesting the determinant is continuous. Do you guys, why is that reasonable to say the determinant is a continuous map from n by n matrices to, why would the determinant, heard it again. Why is the determinant continuous? Well, because it's nothing more than a sum of products of entries of the matrix, right? So if you look at Rn by n as r cross 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 r n squared times, the projection of that determinant, I mean like the, how to say this? Oh, anyway, it's clear the determinant is a continuous map if you look at its formula. We could build that up from more basic theorems, but I'm just going to say that. And so it's the inverse image of, that's an open set, because union open sets. Therefore, GLN is open. Now, in contrast, SLN, which is what? Right, matrices with the determinant 1. In other words, this is the inverse image under the determinant of 1. We know that the determinant's a continuous map. I'm saying we know that. Maybe I should make you a homework problem with that. Maybe test. Maybe the next test should be take home, right? No? Oh. So this is a singleton in a Hausdorff space, namely the real numbers. So it's closed. Inverse image of closed under continuous is closed. Therefore, SLNR is closed. Right? Now, similarly, there's similar things that can be said for GLNC. This is again open. I believe this is an open. This is also open, right? This is also open, but it's the inverse image of what? So the determinant, there's, I'm using determinant for both, but these are really different functions, right? Determinant is an overloaded notation. On the one hand, we're talking about determinant mapping from Rn by n to R, right? But here, we're talking about determinant Cn by n to where? What's the determinant of a complex n by n matrix? C, right. And so we're looking at the determinant of the inverse image of what? The complex numbers with what? 0, the punctured plane, if you will. Well, let me just say 0, right? Complex number 0. Question. Is GLNR connected? Well, the continuous image of a connected set is connected, right? What's the image of GL? What's the image under the determinant of GLNR? It's this. This is the image, right? Under the determinant of GLNR. Is this connected? I mean, it's not, right? This is a set. This is not. This is a disconnected set. I mean, it's a separation, right? I mean, so in other words, GLNR is not connected. What are the two components to GLNR? It's pretty easy. You got the positive determinant ones. You got the negative determinant ones. But GLNR is not connected. How about GLNC? Is this connected? What's that? Yes, because this is connected, right? Because the complex plane with a point deleted is still a connected set, right? You just moved, you've punctured a point. It doesn't disconnect the set because it's two-dimensional. That is true. Let's see here. How to see GLNC is connected? You're saying that's not enough? Right. I mean, that gives us hope. It gives us hope that GLNC was connected. How to actually prove GLNC is connected? Prove its path connected. Okay, very good. You do this, then we'll leave for today. 2 points, 2 invertible matrices, GLNC, right? So you give me the formula. Gamma of t equals to, all right, connect them. Yeah, it would be lovely if we could do this, right? But that seems ill-advised. Because there's no reason, as we let t vary from 0 to 1, that the things that are in between a and b are also invertible. We'd need to prove that they're invertible. I don't know. Is this path connected? I'm not sure. That's an interesting question. My intuition is that GLNC is connected, but how would we show it? That seems like a good question to leave us with for this weekend. So, anyway, I'm sorry. I have so much more to say about quotients. There's the next 2 sections in this book are really interesting, and I'm sorry I didn't get them today. I'm just sorry.